Dear students and participants of this course Railway Engineering, we are going to continue with the discussion which we have done previously, and now there will be some changes in terms of the type of the stresses which get induced in the tracks. So, today our focus will be in the area of vertical stresses, lateral stresses and the longitudinal stresses. If you remember, in the previous lecture we talked about the track modulus, and this track modulus was discussed in two parts. One was the initial track modulus, which is caused due to the seating load, and the seating load was taken as 4 tons in the case of broad gauge and 3 tons in the case of meter gauge. Then we talked about the relief of stresses, and this relief of stresses were coming because there were number of wheels which are moving one after the other, and depending on their distances between each other and the distance of the point of contrafracture with respect to the loading, there is a possibility of the relief of stress in terms of the positive and the negative bending moments which get induced in the rail system. So, that was one aspect which we discussed, and then towards the end we talked about the lift of the rail also, where it was discussed that if there is a loose packing, then the stresses which are being caused, the bending stresses, they can increase by 10% or even more than 10% if the maintenance is not good. Now, today we are going to talk about that various track stresses which are caused due to vertical loads, and whatever these stresses are induced, how they get augmented because of the speed, and then the lateral forces, longitudinal forces and the effect of the curve. So, these are the topics which we will try to cover, starting with the various forces which are acting on the track. So, very first one is the vertical load, and this vertical load includes the dead load as well as the dynamic augmentation which is caused due to the speed, or there may be effect of the hammer blow or the inertia of the reciprocating masses depending on what type of locomotive has been used. Now, these hammer blows or inertia of reciprocating masses, they are more constant towards the steam locomotives, and we are talking about this steam locomotive condition still because we have still 39 such locomotives which are working in the country. The another type of load can be the lateral force, and this lateral force comes because of the movement of the live loads. So, there is a lateral movement maybe because of the track geometry, maybe because of the forces which are working in the lateral direction, and those movements, if they are there, they causes stresses in the rails and the sleepers in the lateral direction, or there may be a possibility that their loads which are being applied, they are being applied at certain eccentricity. Say if we are talking about a rail and there is a curved section, then there is a relative movement of the cone wheel. On the outer curve the diameter is higher, on the inner curve the diameter is lower. So, the distribution of load which is going to be there is uneven. As soon as it happens in this form, the load has shifted from the center of the rail to the side of the rail head, and that will create an eccentricity and will cause its effect in terms of the bending moments or in terms of the component of that as a lateral force. There can also be a case of shunting of the locomotives in the yards. So, there also when it moves from one track to another, there is a lateral force which gets generated. So, there can be similar more conditions where lateral forces may come into play. Then longitudinal forces which can be there, they are caused due to the tractive effort and the braking forces, or in the case of long welded rails, it is also caused due to the thermal forces. So, these thermal forces we will be discussing when we will take up the long welded rails, but this tractive effort we have already talked about, but here we are talking the force created in the longitudinal direction because of that tractive effort, because on the rail when this wheel is moving, so it is putting the effort in this form, and then only it will get a push so that it moves forward. So, it has a component in this direction or a component on the other direction. Then contact stresses which are caused because of the contact of the wheel and the rail section. So, this is a contact area. So, whatever load will be there, it will get distributed through this contact area. So, initially we have P, but now it becomes a intensity as small p. And this condition can also be there because of the sort of distresses and the distress conditions which have got created at the head of the rail, and that is where we can talk about, say, the flat spots on wheels or some other surface defects on the rail sections. So, because of that also the stresses may not only induce but even increase also. So, dead load is usually taken from an axle load diagram. So, that has already been given by Indian Railways. I am not reproducing it here, but this is the one thing which can be there. We have already talked about the axle loads which are coming to the driving wheels on different locomotives. So, that is available and it causes the bending stresses in the rail. So, we will be taking up the bending stresses a bit afterwards. The another thing is the virtual wheel load or the tailboat load, which is basically a dynamic augmentation here. Now, what is this dynamic augmentation? It is actual wheel load or the static wheel load that has to be modified to allow a dynamic augment or impact effect. Now, there is an impact effect in terms of the joints. So, there is a rail joint and then if the wheel comes here, so it has an impact at this point. So, this is one thing, and when it is moving at a speed v, then it is going to be augmented on the basis of the speed. Now, this may be caused due to speed, this may be caused due to the excessive bending moment caused by the leading wheel. It may be because of the hammer blow, as I said in the case of steam engines, or the steam effect, or the inertia of the reciprocating parts, or the effect of the adjoining wheel loads. So, there are different reasons based on the type of the locomotive due to which this can happen. And the longitudinal stresses in the rails are obtained for this particular load. So, whatever longitudinal stresses are there, we have to calculate them. So, let us look at this dynamic effect in terms of the speed. Now, this is obtained by increasing the static wheel load by an incremental amount equal to a speed factor. So, there is a speed factor and this speed factor is also termed as impact factor. So, both are the same thing. So, here say it is being talked an impact factor also. Now, there is an Indian formula which has been used up to 1965 and after that the formula has changed. It was a formula like V divided by 18.2 under root of k, where V is the speed of the train in kilometers per hour and k is the track modulus in kg per centimeter square. Okay. And that was for basically unit deflection. So, in that sense it can be kg per centimeter square per centimeter of the deflection. So, this is the formula which has been used. Now, it has been replaced and what is the replacement is a German formula which was introduced in 1966 and is still in use. What it says is there are two categories of the speed which it talks about. One is up to 100 kilometers per hour and another one is above 100 kilometers per hour. So, in the case of up to 100 kilometers per hour, the speed factor or the impact factor is given by V square divided by 30,000. So, this is the formula which we have to use. Say if the speed is being given as 80 kilometers per hour, then we are going to use this formula. But if it is above 100 kilometers per hour, then the speed factor has two components. One is 4.5 V square divided by 10 raised to the power 5 and 1.5 V cube divided by 10 raised to the power 7, and a difference of these two factors is being considered as a speed factor or an impact factor. So, this is a change which has been introduced in 1966. So, here on the basis of all of these formula, on the basis of the various tests and the research being done, the Indian Railways have these type of graphs wherein you can see that the speed factor has been talked here as 10, 20, 30, 40 going up to 100. When we say this is speed factor, it is a multiplying factor for the static load. So, if the static load is W, then it is W into speed factor. So, if you are talking about 50, it means 50% increase is going to be there. So, this speed factor will be 1.5 in that case. So, that is an augmentation which will be there with respect to the static loading. So, different for different cases these type of curves have been given. As you can see here, this is being given for WDM4, WDM2, WDM1 likewise. So, different such locomotives can be there for which these are provided, and in this case this is for a broad gauge track. Now, just look one of the numerical here. A locomotive has a driving wheel load of 22 tons. It has a permissible speed of 130 kilometers per hour. Then we have to calculate the speed factor. Now, in this case we are going to the German formula, the second formula which has been given, which is 4.5 v square divided by 10 to the power 5 minus 1.5 v cube divided by 10 to the power 7. So, this formula which we are considering here, if we put the value of v in this, what we get is 0.43095. That means 43.09% is the increase which is going to be there to the static wheel load. So, instead of 22 tons, now the effect will be going in form of 1.43 times of that. There is another numerical here. Here it says that the driving wheel load is of 22 tons. It has a permissible speed of 130 kilometers per hour. Track modulus is being given as 100 kg per centimeter square. So, this track modulus was used in the Indian formula which was in use up to 1965. So, we are considering that formula here, and based on that what we get is V is 130 divided by 18.2 into K is 100 kg per centimeter square under root of that. So, the factor comes out to be 0.7143 or 71.43%. Now, if for this given condition of 22 tons and with a permissible speed of 130 kilometer per hour, the same thing which has been looked here in the numerical one, there what we got was 43% as the speed factor. That means, if we keep using the Indian Railways formula which has been stopped in use in 1965, then there the value is coming 71 or 72% as compared to a 43%. A big gap is there in these two values. So, a comparative assessment can also be made in that way. Now, another dynamic effect can be in terms of a hammer blow. Now, what is hammer blow? Now, here you can see there is a case of a steam locomotive being shown. These coupled wheels are there, and when it is moving ahead, then these crankshafts which are being provided, which are connecting the different wheels, they keep moving sometimes up in this form or sometimes down in this form. So, there is a movement of these coupled systems or the crankshafts in this way. So, there are loads which are being placed on all of these locations, and these loads are basically revolving in this form. So, these revolving masses which are crank pins, connecting rods, coupled rods, bolts, etc., in the driving and the coupled wheels, they revolve eccentrically with the wheel, as you can see on the side. So, they are not moving just at one point, the distance, there is a change in the location. So, that change in the location is causing that sort of an eccentricity here, and because of that this effect is coming. The effect of these masses is counteracted by balancing weights which are placed at the opposite side of the crank, because they are creating the bending moments, they are creating maybe the torque conditions also in this case. Now, the horizontal component of this gets balanced out by the horizontal component of the centrifugal force. So, when we are talking about the centrifugal force which is acting outwards, now if we take the components of these in the form of either the horizontal and vertical axis, wherever the disc is being placed in certain way. So, there is a balancing effect which is going to be there. Now, vertical component of the force remains unbalanced, horizontal component gets balanced. This vertical component of the force when acted in the downward direction adds to the wheel load and causes hammer blow on the rails. So, as we see that if this is going in this form, so what will happen is, so this is a component which is coming and that is going to create more effect on the rails. So, more load is coming down, the wheel load along with this particular load is acting downwards. Whereas, if we are talking about another case, then here it is an upward condition which will happen, and therefore, it is going to create a sort of a relief. There is a lift which will be caused at that particular location. So, it is acting in two different directions depending on how the movements are there of the crankshafts and the coupled systems. The magnitude of the hammer blow on the rails can be computed as m divided by g into r into 2 pi n square and sin theta, multiply it with that, where m is the net overweight in kgs, r is the crank pin diameter in meters, n is the number of revolutions of wheel in seconds, and theta is the crank angle. So, if those values are known to you, you can calculate the amount of hammer blow which is going to be induced in these cases. The another one is a steam effect, and again this is related to the steam locomotives. Now, how it is being caused? When you are talking about the steam effect, it means we are talking about a case where there is a encasement in this form, and then the plunger is moving inside it of a diameter, previously as we talked about small d, with a cross sectional area of A, and then there is a pressure at the back and the front. So, there is a difference in the pressure which is going to be caused, and the length on which this is going to move is the stroke length, that is L, we considered. So, it is caused due to the steam pressure on piston which is transmitted to the driving wheels through crank pins and connecting rods. So, whatever pressure is there, on the basis of this pressure and more difference is there, then more faster it is going to move, as shown in this video given to here. Now, the vertical component of the crank pin and the connecting rod is at an angle with the piston rod, and the force adds to the wheel load when the crank pin is in the downward direction and subtracts the effect of the wheel load when it is in the upward direction. So, considering that how these crank pins are moving, as you can see, sometimes it is going up or then it is coming down. On the basis of that, there is a positive or negative condition being created in terms of whether it is going to get added up or it is going to get reduced with respect to the initial load or the static loads which are there through the wheel system. So, this is not in synchronization with the hammer blow caused due to balanced weight. So, they are working at different points of a time, and therefore, at one time if there is an effect of the hammer blow, then another time there is going to be an effect of the steam. This vertical component is given by the formula as given here, which is pi r square into p and multiplied with r sin theta plus minus h divided by L, where this plus minus h plus minus is going to be with respect to the way the movement of crank pins is there, or whether it is going to create a positive or a negative condition. Now, here L is the length of the connecting rod in meters, r is the crank pin radius in meters, theta is the again the crank angle, p is the pressure. So, rest of the things we already have discussed. So, p is the difference in the pressure in kg per centimeter square at the front and the back of that piston which is moving in the cylinder, and h is the height of the cross head above center line of the driving wheel. So, whatever is the center line of the driving wheel and this cross head, how much it goes up. So, this is the head which we are talking here. So, this small h. Then another case can be the inertia of the reciprocating masses. Now, in this case, what is being defined as the effect of inertia of the reciprocating masses and the acceleration caused changes pressure on the piston and hence also changes the force in the connecting rod during the revolution of the wheel. So, this inertia which is there, it is basically creating an impact in terms of the pressures get generated. So, delta P is going to be changed, and this delta P is also being used here. If you see that this is a P which is being used here, and it is also being used previously. So, if this pressure is changing because of the reciprocating masses, and reciprocating masses already, as we can see in this diagram, there are reciprocating masses, they are continuously moving around with respect to the center of the wheel. And this component is given by a bigger formula, that is m divided by g. This is one value multiplied by r multiplied by 2 pi n square of that, and then multiplied with cos theta plus r divided by L into cos of 2 theta, and then r sin theta plus minus h divided by L. So, the whole of the thing has been incorporated here finally. What you can see, previously here we talked about pi r square into p into r sin theta plus minus h divided by L. So, we are talking about r sin theta plus minus h divided by L here, and then before that we talked about m divided by g into r into 2 pi n square into sin theta, but now we are taking a component. So, 2 m divided by g into r into 2 pi n whole square multiplied by sin theta, that actually we have replaced with cos theta plus r by L into cos of 2 theta. So, here m is the mass of the reciprocating parts, L is the length of the connecting rod, n is the number of revolutions per second, theta is the crank angle, h is the height of the crosshead above the center line of the driving wheel, and all of these things we have already talked previously. Now, coming to the lateral forces. Lateral forces we have talked previously also. This happens because of the oscillations which get sets in the axles, and which causes the striking of the flanges of wheels with rails, and this type of action is known as nosing action. So, we have a rail provided here, and similarly a rail is provided on the other side, and then there is a flange in this form. So, there is always a gap, a clearance is there with respect to the rail head. Now, if there is a movement of this system either way, maybe the left or the right, then this flange is going to hit on the side of the this rail head. So, this is another issue. Now, this lateral force, it produces the lateral deflection. So, there is a possibility that it gets deflected in this form, or a horizontal bending of the rails. So, the bending of the rails will also be a possibility, because it is in this form being placed at the top of the sleeper. So, because of this, then the bending action will be there. The twist in the rails can also be caused. So, there is a bit deorientation of the rail, and the bending of the head and the foot of the rail, that is another possibility which may happen depending on what is this lateral load, what is the value of this, how much big it is, and this is resisted by the rail sleeper fastenings, as I already shown here. They are the fastenings being provided, or the friction between the rail and the sleeper, and as well as the ballast cover. All of these things are going to try to keep the system in place. Now, this total lateral force which is exerted by the rolling stock is algebraic sum of flange force and the friction between the wheel and the rail. That means, you have to consider it with respect to their nomenclature. And when wheel flange presses against one of the rail, the friction on the other rail resists the lateral movement because of the rigidity of the wheel base, because they both are being connected with each other, as well as because here if the diameter is increased and here the diameter has gone down, then it will try to come back to the normal situation, and it will try to work on the average diameter. Now, 50% of the total lateral force is considered as acting on the rails, and in the case of a design, the design load against the horizontal thrust is taken as 40% of the axle load or the static wheel load. So, whatever this axle load is given, say it is 20 tons of axle load is being given, then 40% of that, that means 8 tons is going to be considered in the design. And this can be up to 2 tons as a additional value which may be there, and this is a Indian Railways practice. As per the new practice, it is taken from the Prudhomme's formula, which is lateral force is 0.85 into 1 plus P divided by 3, where P is the axle load in tons. So, if it is P is say 21, so 21 divided by 3, so 7 plus 1 8, 8 into 0.85. So, that is the value which will be there. Then another one is the longitudinal force, which is caused due to the tractive effort of the locomotive. We have already discussed about it, that the rail section is provided and then the wheel is moving at the top and it has to move in this direction. So, tractive effort is going to act in this way. So, there is a tractive force which will be working, and this reaction will help the wheel to move ahead. Similarly, there can be a braking force. So, if there is a braking force, the brake force will apply in this way. So, there is braking force and there is a tractive effort condition, or there is a temperature variation in the welded rails. So, that means the rail is going to move. So, there is an elongation or contraction which will be there on the basis of the temperature. So, these are the 3 cases because of which there is a longitudinal movement which may take place and the longitudinal force will get induced. Now, these longitudinal forces on account of the tractive effort for the AC condition, that is being taken as 30 to 40% of the weight of the locomotive. So, in the electric traction, it is taken as 30 to 40% of the weight of the locomotive. If you are talking about the thermal stresses which are being caused because of the change in the temperature, then this is 10.75 kg per mm square in winter, which is tensile in nature due to contraction, and 9.5 kg per mm square in summer, which is compressive in nature. So, these are the values in terms of a thermal stresses which will get induced in the rails. And here we are talking about the broad gauge system. Then another thing is 15 to 20% of the weight of the locomotive and 10 to 15% of the weight of the trailing load is what is being taken when it is on the account of the braking force. So, thermal force we have talked about, then we have also talked about the braking force, and in the case of tractive effort we have also looked at. So, if the tractive effort case is 30-40%, in the case of thermal it has a value as 10.75 or 9.5 depending on the season, and in the case of braking it is 15 to 20% of the weight of the locomotive and 10 to 15% of the weight of the trailing load. When we say trailing load, we are talking about the wagons which are at the back. So, both will be working separately. So, weight of locomotive and weight of trailing load. And the last thing which we can talk here is the stresses which will bear due to curve. The causes which are here is the lateral bending due to rigid wheelbase of the vehicle, because in this case if they have been connected in this form, then the movement which is being taken up by the front one is not the same as being taken up by the rear one. So, this is the front axle and say this is the rear axle. So, there is a change, and because of this change what will happen, the more pressure is coming on the inner wheel where it is trying to give pressure on the outer wheel in the case of front axle. So, this type of issue can be there. Excessive vertical load over the normal wheel load on the inner or outer rail depending upon the super elevation and the speed of the wheel, because here this is a centrifugal force acting, and so as to counter that, this rail section has to be in this form. So, it means there is some height h which is being given, which is defined as super elevation. So, this is another thing which will be there. So, excessive loads are going to be there depending on whether the super elevation is correctly given or not, or if the speeds are higher, then also that will be the problem. And there is a non-uniform distribution of pressure over outer and inner wheels. This is obvious, as I said, that here the pressure is more. In the case of the rear, the pressure comes on the inner side, whereas this inner wheel on the front axle and the outer wheel on the rear axle is not facing that much pressure. So, that non-uniform things are there, it means the stresses are going to be induced here. In the case of surface defects, it is caused due to the unevenness of the ballast or the subgrade or the uniformity in the gauge or the level difference in the top of the rails. So, these are the 3 cases which are totally related with maintenance of the track. So, if there is a problem with the maintenance of the track, then the stresses again gets induced. We already talked about that if the rail seat is not properly fitted, then the lift will be there and that lift is going to create a negative stress, or the bending stress increase will be there by 10% because of that lack in the maintenance. A surface defects causes deflection as high as 1.5 times the depth of the flat or the low spot at critical speed of 30 kilometers per hour. Okay, so whatever deflection we did talk about, it gets enhanced because of the problem, because of the bad maintenance which has been taken here. Additional bending moment is also caused, which is something like 370 tons per centimeter for broad gauge with a route which is being operated by WDM for locomotive. So, these are further other type of stresses which can be there, which needs to be taken into consideration when we are designing the overall track taking various components. With this, we close our discussion now on the track stresses. We will be continuing forward. What we discussed was the various track stresses which are being caused due to the vertical loads, then the augmentation of those static loads because of say the speed, because of the hammer blow, because of the steam, all those reasons. And then we talked about the longitudinal forces, the lateral forces, stresses due to the surface defects, curves, etc. We will be meeting again in the next lecture. Till then, bye. Thank you.